phenol's interesting compound has two functional groups. One is in both parts are nucleophilic. One is hydroxy group's nucleophilic. The other one, the aromatic ring, is nucleophilic. The nucleophilicity of aromatic ring we have seen in chapter 13 is because of the aromatic ring has many pi electrons, and the pi electrons, they are generally nucleophilic, and similarly, hydroxy group has this lone pair on it, on oxygen, and the lone pair makes oxygen atom, nucleophilic as well. Okay, so if I ask you, just if you look at the isolated CC double bond and isolated hydroxy group, which one is more nucleophilic? The double bond is more nucleophilic, or the hydroxy oxygen is more nucleophilic? Just, they are not linked. Just a separate carbon-carbon double bond and hydroxy oxygen. Which one will be more nucleophilic? If I ask you, just make a choice. But to answer the question, you think about, whether if double bond nucleophilic means the pi electrons will be donated, okay? And if the lone pair is the oxygen nucleophilic, then the lone pair is donated. So the question is basically really boils down to which kind of electrons are more reactive. You think it's the pi electrons in the double bond or lone pairs? Which one more reactive? Lone pair, very good. Your sense is right. In the lone pairs, they are non-bonding one, and the pair of electrons in the pi bond is the bonding electron. Bonding electrons, they are more stable than the non-bonding one. So if you just directly compare a pi bond, regular pi bond, and a regular hydroxy oxygen, the hydroxy oxygen is more nucleophilic. Okay. So and also if you look at the resonance forms of the phenol, we can write the four resonance forms. But when last class when we discussed it, I did emphasize this form is of greater importance than the rest of four forms, because this form is more stable, because this form is aromatic. So all these forms have the same number of chemical bonds. All those four forms have the same number of chemical bonds. But this one is aromatic. Being aromatic means the structure is roughly 100-something kilojoules per mole more stable than the rest. So this form is much more important than the rest. So the importance of this one is probably more than all those three forms combined together. Okay. So that means the oxygen lone pair mostly on oxygen, only small amount of delocalize to the ring. So if you really look at nucleophilicity of the double bond and the nucleophilicity of the oxygen atom is more nucleophilic. Okay, and then now because of the phenol has two nucleophilic parts. So how do we know which nucleophilic part will be reacting with the electrophile, give you the product? So there's two situations. One is the one of ring carbons, okay, will be bound to the electrophile. This we call C substitution. Okay, it's just one of ring carbon atom will be acting as a nucleophilic atom. The second case is the oxygen with lone pair on it will be acting as nucleophilic atom react with electrophile. Those are called O substitution. So because oxygen atom is generally more nucleophilic, that means if phenol is allowed to react with an electrophile, it will react faster at oxygen compared to carbon. So if the reaction is under kinetic control, O substitution product dominates. And what kind of situation we say reaction is kinetic control? that means the reaction is far away from the equilibrium. So usually, when a reaction is slow, okay, it's under kinetic control. Okay. Now under thermodynamic control, the C substitution dominates. Why? Because our C substitution product is more stable. Here, I just give you some example. Those are three, the isomers. Okay, both can be formed by, the phenol react with, the alkylation agent. This provides this acyl group. Okay. So all those are isomers. Okay. So this is O alkylation product, means oxygen bound to the carbonyl carbon. Okay. And those two are C alkylation product, means the ring carbon bound to the carbonyl group. And you see that, look at the formation enthalpy. The formation enthalpy is basically tell you the stability of a compound. So the greater negative formation enthalpy you have means the particular structure is more stable. So obviously what you can see, these two C alkylation products, they have somewhat similar stability, with this guy a bit more stable, but both are a lot more stable than the O alkylation product, because the O alkylation product has a less negative formation enthalpy value. Why that's the case? Because of in the C alkylation product, the ring double bonds, okay, is in conjugation with the C double bond. You see that double, single, double. So this is in full conjugation. Okay, so this allows better electron delocalization. So that provides much better, the environment for electrons to distribute. Same thing here. This C alkylation product. Still, you see CO double bond, single bond, double bond is in conjugation with the ring double bond. Okay. Look at here, the double bond is not in conjugation with the ring double bond. Okay. So you don't have electronic communication between the carbonyl group and the ring double bond. Same argument if you look at the alkylation product. Okay. Alkylation product, let's say we just using. I didn't want to do that. Okay. So alkylation product, if we compare these two guys, these two guys are isomers. Okay. Same reason, this guy will be more stable. The top one will be more stable. Okay, more stable. Why? Because the top molecule, the alkyl group, okay, can electronically communicate with aromatic group. Because we know, if we recall what we learned in chapter 13, alkyl groups, they are activating group to the aromatic ring in the electrophilic aromatic substitution reaction. Why is activating? Because this sp3 carbon can donate electrons to the ring. Okay, so this electronic communication also encourages electron delocalization. So for the same reason, this one also is more stable than this one. Okay, but anyway, basically for all the situations, the C substitution will be more stable than the O substitution, because of C substitution allows aromatic ring directly communicate with substituent, so give you more stable product. Okay? So because of C substitution is more stable, so if the reaction is under kinetic control, the C substitution dominates. So what is kinetic control? Means the reaction rates are the reaction rate is fast enough so that you only need to consider stability of possible products. So that's called thermodynamic control. So the thermodynamic control usually can be achieved by whatever way they can make reaction faster, means higher temperature, okay, can make reaction faster, right? Or you have very powerful catalyst can speed up a reaction. So just, if you're looking for thermodynamic control, either very high temperature, okay, or very powerful catalyst can speed up a reaction. Okay? And the kinetic control means, lower temperature slow down the reaction, or I don't have a catalyst, or I just using relatively weak catalyst. So that's basically the general line of this discussion. Okay? So now, first thing is there's many kinds of electrophiles. If the some electrophiles, the electrophilic atom is not carbon. So there are a few examples we have seen so far. One is a halogen. The electrophilic atom is not carbon. And the other one is a nitrogen cation, NO2 plus. The electrophilic atom also is not carbon. And also we have the SO3, the foundation, also electrophilic atom is not carbon. Why electrophilic atom is not carbon? Only C substitution product forms, because of the O substitution product is too unstable. Okay, so just imagine, if the bromine connect to O, that product looks just odd. Okay, it can form, but very unstable. Okay, so when the electrophilic atom is not carbon, you only see C substitution. Like in this case, if you want to do the halogenation, you just treat it with the halogen, and and you don't need a catalyst anymore. Why? Why you don't need a catalyst here? If you use benzene, you need a catalyst, but here you use phenol, you want to do the halogenation, you don't need a catalyst. Can anyone tell me? You learn something chapter 13, probably can tell me why here you don't need a catalyst. If you just benzene, you will need iron bromide, okay, and catalyst to do bromination. But here you don't need. And actually, the measures must be taken to slow down the bromination reaction. So how do you slow down reaction? First, cool it, keep at a low temperature. Second, using a non-polar solvent. Okay, so those are the using of this solvent and the low temperatures try to slow down the halogenation reaction. Because if you don't use this kind of way to slow down the reaction, you actually could get the polybrominated product, and it means they have multiple halogen installed. Okay, multiple halogen installed, and they eventually can lead to some other side reactions. So why we need to slow down this reaction instead of speed it up? Can anyone tell me? Let me see. Sandy? Well, if we slow down and try to make it kinetically favorable. But this is not the reason. Okay? You see, first you have to find out why this reaction is so fast. Right? You see, if you're using benzene, you brominate it. You need an added catalyst, because without catalyst, the reaction will be too slow. So did you see difference here? You have the OH group. OH group is what group? Activating group. Okay, it's actually a very powerful activating group. So this thing halogenation like 1,000 times faster than benzene itself. So if you don't using this non-polar solvent and cool down, this reaction could go very, very fast, and the increased reaction temperature can lead to side reaction and the polyhalogenation. Okay? And why non-polar solvent can slow down the reaction? Because electrophilic aromatic substitution involves an ionic intermediate called sigma complex. I hope you recall sigma complex formation is rate limited, and the intermediate is ionic. If it's ionic intermediate, its formation will be faster in a polar solvent. Okay? So we are using a non-polar solvent or weakly polar solvent to slow down the formation of the reaction. Anyway, similarly, here is a kind of phenol using the you know the mixture of sodium nitrite and the sulfuric acid. This combination provide you a nitrogen-based electrophile. Is not NO2 plus, is actually NO plus. Okay. But anyway, this electrophile is also not carbon-based, so you only get a C substitution product. Or if you want to do nitration, you just treat phenol with nitric acid. Don't need sulfuric acid. Again, you don't need sulfuric acid. And actually, you need to careful keep the reaction cool to slow down the reaction, so you don't get the polynitration product or some further complication. And what you see is a nitro group can install on the ring. And in all cases, OH group is OP director. And I hope that's what you recall in chapter 13. OH group is OP director. So if the P position available, usually electrophile will connect to the P position. If P position is not available, well, it connect to O position. Same thing here. The P position is not available, so connect to O position. Okay? If the P position is available, we'll connect to the P position. Because OP director. So similarly, the sulfonation can also be done. You don't need SO3 to speed up reaction because OH group is activating group. Okay? So anyway, if the electrophile is not electrophilic atom is not carbon-based, is not carbon-based, you always see C substitution because O substitution is a product too unstable. Okay? Now in a Friedel-Crafts reaction, we know that in Friedel-Crafts alkylation or Friedel-Crafts acylation, in both cases we have the carbon-based electrophile. In case of Friedel-Crafts alkylation, the real electrophile here is carbocation. Okay? In the Friedel-Crafts acylation here, the real electrophile is this one. Okay? Azocation. Okay? In these two cases, if the reaction conditions promote the formation of carbocation or ethylene cation, then you will see the C substitution product because of those reaction conditions needs pretty powerful catalyst, like if the reaction condition allows the formation of carbocation or the ethylene cation, then those reactions will allow the reaction to establish thermodynamic equilibrium. So you will get the C substitution product because C substitution product is more stable. Again, because the hydroxy group is OP director, usually we'll prefer to occupy P site. If P site is not available, then we'll try to occupy the O site. So you see the phenol react with this guy. P site is a major product, but O site still some. But always, because both those reaction conditions, this reaction condition, tertiary butyl acid, promotes the formation of carbocation. This is real electrophile. And in case of Friedel-Crafts acylation, you always need the use of aluminum chloride because when you use aluminum chloride, you will react with acyl chloride and give you a carbocation. So when if you have this ethylene carbocation or alkyl carbocation, you will see C substitution product. Now, under what condition you will see O substitution product? Under the one kind of O substitution product is basically you carry out the reaction between the phenol or its conjugate base with electrophile in the absence of catalyst. You don't have a catalyst, so the reaction, you don't have a catalyst, the reaction is less likely it could be happening at a condition far from the equilibrium. That means that the kinetic control. So one of ways to do such a reaction is you convert the phenol to its conjugate gas called phenoxide. Okay, then let this phenoxide react with electrophile. So this is mostly common done by the treating phenol with a base, because the phenol is quite it's about 1,000,000 times more acidic than alcohol. Even potassium carbonate. Okay, potassium carbonate is considered a very weak base. Potassium carbonate is strong enough to a strong enough base to remove a proton from phenol. So when you see the phenol react with something with potassium carbonate, this potassium carbonate actually will remove a proton from phenol, give you the potassium phenoxide. And the potassium phenoxide is a fairly good nucleophile. It's just like alkoxide, similar. Okay? So if with alkoxide is a good nucleophile, if you have alkyl halide, appropriate alkyl halide, then you could see SN2 reaction. When we say appropriate alkyl halide, usually means that the alkyl halide is primary, master, or equivalent one. Because if you have secondary or tertiary, what else will be happening? If you have a secondary or tertiary halide, what will be happening? If you have electrophile react with a nucleophile, you always consider two. You always think about two possibilities. One is a nucleophilic reaction. The other one is elimination. Do not forget that always, have to think about possibility of elimination. And for primary alkyl halides, or even more reactive alkyl halides, the reaction will mostly give you substitution product. But if you have a secondary or tertiary alkyl halides, you will see elimination as a major product. So that's something you always have to think about. Okay? Here's one example. Phenol, once in potassium carbonate acetone. Acetone is solvent. Potassium carbonate is the base. So the phenol react with the potassium carbonate will give you potassium phenoxide. This is this one. Okay? And then phenoxide will react with allylic bromide. Allylic bromide is one of the best, the electrophile for SN2 reaction, because two reasons. One is this electrophilic carbon is primary, so stereohedrous is small. Second is this bromide is very unlikely to undergo elimination reaction, because the beta proton here is a vinyl proton. If it did undergo elimination reaction, it would give you accumulated dying. It's very unlikely to happen. So this reaction is for this bromide is a very reactive electrophile for SN2, and it's very unlikely to undergo elimination. So it's one of the best the substrate for SN2 reaction. What you see is the alkoxide oxygen is acting as nucleophilic atom, react with the electrophilic carbon, give you the O substitution product. So here the reaction condition does not promote the formation of carbocation or ethylene cation. So the reaction actually happens far away from equilibrium. The reaction under kinetic control. So you see O substitution product. And the other kind of O substitution product can be obtained again by carrying out the reaction at a condition far away from equilibrium. One way we can do it is, okay, we have a phenol, okay, we directly react with acyl chloride. Difference here, we don't use aluminum chloride. Just directly react with phenol. No, acyl chloride. Okay, we don't use catalyst. So if we don't use catalyst, the reaction is sort of slow. Okay, but often we can add pyridine here. Okay, the purpose add pyridine is to remove the formed HCl here. So that can give us, because of we don't have a reaction condition to encourage the formation of ethylene cation. So the reaction is under kinetic control. So you get the O alkylation as major product. Because of the oxygen atom is more nucleophilic than ring carbon. So the oxygen atom react with electrify faster than the ring carbon. So the O alkylation product forms faster. Similarly, phenol can also react with anhydride. This reaction can be assisted by an acid, and we don't need to talk about mechanism here, okay? Or the reaction can be assisted by a base, okay, sodium hydroxide. But in both cases, because we don't have aluminum chloride here, so we don't see the formation of this guy. So as long we don't see the formation of this guy, so the ethylene cation, we don't have this. We don't have this, okay? Because we don't have this, the reaction, it still happens at a condition far away from equilibrium. So it's kinetic control. So you see O alkylation product. And what you see the difference here, if you want to Friedel-Crafts reaction, you need the reaction condition to encourage, in this case, carbocation formation. Here, you need to encourage, the formation of the ethylene cation. And those reaction conditions, okay, bring the reaction close to equilibrium. That's why you see the C substitution product. And now if you look at let's say combination of phenol and how many carbons? So the 8 carbons. If you have these two guys react, okay, so if you let these two guys react in the absence of aluminum chloride, and we know if without aluminum chloride, the oxygen atom here is more nucleophilic. So this guy will form faster. The reaction under kinetic control. So this one will be the product. Okay? If these two guys react in the presence of aluminum chloride, and we know the aluminum chloride, if you forgot, go back to chapter 13 to check again. Aluminum chloride will react with acyl chloride because aluminum chloride is a powerful Lewis acid, and will take one chloride away, give you an ethylene cation. And that ethylene cation will react with the ring. And because ethylene cation is a highly reactive species, so the use of aluminum chloride actually helps the reaction to achieve equilibrium state. That means you will be getting a more stable product. That's why you will be getting this this product, C alkylation product, as a major product. The interesting is, okay, let's say if you do this the reaction, carry out this reaction, okay, in the absence of aluminum chloride, you will get this one as a major product, okay? And you isolate it, okay, you get a pure the O alkylation product. Then if you treat this O isolation product with aluminum chloride, this one will isomerize into this guy. Why that's the case? Because aluminum chloride, okay, here is a powerful catalyst, okay. It can, promote the formation of the ethylene cation, even from this one, okay. So the what you can think is the basically, the even you have this, right? Then the this one you have the, lone pairs, okay. So the oxygen, you also have lone pairs here, okay. So the you can bond to the aluminum chloride. Then this complex, okay, can break off. And then the we're gonna give you the, the ethylene cation, okay. Then ethylene cation can act as an electrophile, react with the, react with the, aromatic ring, okay. Here, obviously, you will react with OP side, okay. So it is just standard electrophilic aromatic substitution reaction. So then you have the standard electrophilic aromatic substitution reaction. And eventually lead to the C oxidation product. Because of C oxidation product, is more stable than the O oxidation product. So this kind of reaction called Frey rearrangement basically describes that aluminum chloride catalyzes the conversion of O oxidation product of phenol into the C oxidation product.